Auction Pricing of Network Access for North American Railways, presented by Dr. Stephen Herod at the 2012 Informs Annual Meeting in Phoenix, Arizona. Welcome. This presentation is motivated by the desire of many nations to introduce competing commercial railway services on shared railway lines. In North America in particular, political objectives demand that the negotiation and enforcement of contracts for transportation services be transparent. Auctions are frequently used as a selection method between competing offers for transportation services, but are they appropriate for the likely North American railway case? In this research, the method of evaluation is a fixed increment bid auction, where optimal selection of offers is assured at each round through computation of a feasible timetable. At the end of this presentation, we will see that pricing transportation infrastructure by competitive bids leads to a loss of value by the infrastructure owner, and that longer auction cycles lead to even less revenue. Shared use of a railway line requires a timetable, both to define contractual commitments and to maximize utilization of the railway. A timetable defines the path that a train will take on the railway line and the timing of the train during its journey. An important task during timetabling is to ensure that the train paths are mutually feasible and conflict-free. Each train must have track allocated to its journey, and care must be taken to design the train path so there are no path conflicts. A significant question in pricing of railway line paths is how a train path should consider conflicts with other trains in its pricing. For example, in the figure, a contract for train path ED obstructs the sale of a train path on AB. Consequently, the price for path ED must consider not only the consumption of the railway line on that path, but the lost value of the path AB. A number of pricing methods for railway services exist in practice and in the literature. The first and oldest method is to simply allocate railway line cost to a train path according to accounting principles, according to average allocated cost. Another frequently used method is to price according to the marginal cost of using the railway line, including only those costs that are directly attributable to the train path. A value of service approach fixes prices according to predetermined estimates of the value of the service provided. A value of service approach does not discriminate in pricing between different buyers. On the other hand, yield management specifically discriminates between buyers according to their willingness to pay. And finally, an auction method, where prices as assigned by open competition between buyers. In the United States, many interest groups cite specific policy goals for future passenger railway operations. These goals are to eliminate government subsidy, eliminate perceived inefficiencies in government-operated services through entrepreneurial innovation, and to stimulate new services by encouraging innovation and commercial experimentation. In summary, political goals seek greater involvement of independent commercial transportation providers, but because inevitably this process will be government supervised, or even place the government in the role of seller of train paths, it is necessary under U.S. government practices that this process be transparent. This figure summarizes the pricing models according to their transparency and relationship to underlying accounting costs. The auction method of pricing is evaluated here because it offers a transparent pricing mechanism that is independent of the underlying costs and is revenue seeking. The implemented fixed bid auction follows the method of Borndorfer et al. 2006. First, all train path requests are considered at their opening bid, and an optimal, revenue maximizing, and conflict-free selection of train paths is returned as a timetable solution. Some trains will not be included in the solution because the railway network is saturated and does not have any further capacity for trains. Then, the trains left out of the solution are evaluated, and their bid prices are increased by the amount of the programmed bid increment. The timetable is solved again, producing a new set of optimal train paths and possibly removing some previously assigned train paths. The cycle is repeated and the process is stopped when all trains not currently in the solution have reached their maximum bid. The last solution is the returned timetable and price list, and the auction is ended. This method was tested over 20 replications of train path allocation problems. In each problem, the train speeds were randomized, and the revenue forecasts or buyer's utility for each train path were also randomized. The railway line is a single-track line, typical of North America, which has a nominal saturation capacity of 8 trains. Each replication has 14 bidders, that is, 14 train path requests, so the demand exceeds network capacity by a factor of 1.75. Trials were repeated for these 20 replications at 6 levels of bid increment, from 10% to 60%. For example, at 10%, each time a train path request sought to increase its bid to enter the solution, it increased its prior bid by 10%. In this slide animation, the timetable solution at each round of the auction is displayed. Note how some trains enter and leave the solution at each round, and how the network consumption changes. Finally, in the last step, the bottom diagram is the first solution timetable, and the top diagram is the auction end solution timetable. The similarity between the two timetables is coincidental. Sometimes they can be similar and sometimes they can be completely different. Two key questions are considered in reviewing these results. How significant are infrastructure conflicts in limiting revenue, and how significant is the auction process in limiting revenue? This slide presents the results, averaged over 20 replications and indexed by bid increment. The size of the bid increment has a modest impact on results, but note that smaller bid increments lead to lower train path prices and reduced seller revenue. The top line in the figure is the average over the 20 replications of the top 8 bids, or the most valuable 8 train paths, without regard to network capacity. Below that is the same value for the top 2 through 9 bids, reflecting that in an auction everyone pays the last highest price of their competing bidder. Below that is the actual optimal train path selection if the true bidder values were known, and sales were made at those prices without an auction process. Finally, the lowest line is the actual realized revenue through the auction process. The difference between the no bid and the auction revenues represents the value lost from the railway line owner by selling the train paths instead of operating those train paths themselves in a vertically integrated transportation company. In conclusion, the auction process achieves one critical goal, that of providing transparency to the shared marketplace for transportation infrastructure. However, the auction process favors the buyer or user. By disintegrating the railway operations from a vertically unified firm to a separate infrastructure operator and independent train operators, approximately 15% of the potential value of the train paths is foregone and transferred to the independent operators. Finally, the auction system may lead to an unpredictable service mix. Under the auction system, there is no assurance of the nature of the transportation services the winning bidders will provide. For example, there is no commitment that the train path will be dedicated to freight or passenger service. Thank you for joining me for this presentation of auction pricing of network access for North American railways.